Gadolinium-doped ceria (GDC) is paving the way for the next generation of fuel cells. By optimizing GDC from bulk synthesis to thin-film half-cell integration, we unlock commercial breakthroughs in intermediate temperature solid oxide fuel cells. The challenge in SOFC commercialization lies in overcoming thermal bottlenecks. Conventional ITSOFCs require high temperatures, but our target ITSOFCs operate efficiently at lower temperatures, enhancing performance and lifespan. Gadolinium-doped ceria offers large channels for oxygen ions, making it ideal for SOFCs. However, high conductivity can lead to short circuits, necessitating precise control over its operation and synthesis. Our research architecture involves three phases: bulk optimization, thin-film feasibility, and half-cell integration. Each phase is crucial for maximizing ionic conductivity and ensuring successful integration. In Phase 1, we focus on bulk synthesis using solid-state reactions. By optimizing the gadolinium doping percentage and sintering temperature, we enhance ionic conductivity and material density. The doping matrix reveals that 10% gadolinium offers the highest ionic conductivity and optimal grain size. This balance is crucial for minimizing surface diffusion and maximizing performance. Achieving a dense electrolyte requires precise sintering. At 1773 K, we reach near perfect density, enhancing the structural integrity and efficiency of the GDC-10 electrolyte. Transitioning to thin-film electrolytes addresses the limitations of bulk ceramics. By reducing thickness, we improve functionality and efficiency, paving the way for advanced SOFC designs. The spray pyrolysis technique allows for the creation of high-quality GDC-10 films. By optimizing variables like droplet size and carrier gas, we achieve dense, crystalline structures without carbon contamination. Phase 3 tackles the challenge of integrating GDC-10 into functional half cells. By engineering the chemical interface, we prevent peeling and ensure a robust, adherent film. The precipitative deposition method revolutionizes integration by modifying surfaces, enabling low-temp wet deposition, and phase-lock sintering. This ensures a durable and cohesive structure. With a thickness of approximately 13 micrometers, the electrolyte layer acts as an effective barrier while maintaining electrical resistance. This balance is key to enhancing SOFC performance. Our GDC Neo GDC half cell achieves the commercial benchmark of 0.1 S per centimeter at 500 degrees Celsius. This success underscores the effectiveness of our interface quality and deposition techniques. By optimizing material, innovating methodologies, and engineering substrates, we bridge the gap between raw materials and functional half cells, making GDC a reality for commercial applications. The successful development of GDC-10 films and half cells marks a significant milestone. This blueprint offers a scalable solution for the commercialization of intermediate temperature solid oxide fuel cells.